is shocking. In my opinion, is one of the most shocking thing, and is perhaps the most astonishing conclusion of modern physics, which is we now are here. Okay, move a little bit. What now means? What is the meaning of now? Well, I know what is the meaning of now for me. You know what is the meaning of now for you. Is it the same now? Thank you. Thank you for this very kind introduction. The first thing I have to do is to pull out this, which I've prepared before you came in. Let's see if it, yes, sorry, which I'm going to use. And that would be my high technological equipment to talk about time. That would be my metaphor of time, right? Time is a long line. There is a present, there is the past, the far past, the more far past. This is 10 minutes ago, this is yesterday, this is last year. Down there is Big Bang, this is tomorrow, and the future we don't know. So this is a metaphor of time. We're sort of here. We have 1 hour, whatever, with questions and so on, so we're going to cover that. And I'm going to tell you that time is not like that. That would be the message. So what I want to do is to give you a sense of where I think we are about understanding of this strange, mysterious things, which is time. It will be sort of a journey. For me, time has been an open question from my early years as an adolescent, from all the way through my studying of physics and then into my work as a physicist. It's been a sort of obsession because quantum gravity requires us to rethink what is time. I've been going around this question: what is time? So in the book and in what I want to tell you tonight is a bit of a synthesis of that, where we are, what we know, what we think is true, including the parts that we don't yet know, we are confused about. And I will do it as taking you to a sort of journey which is back and forth. So I'll start from this idea of time, this long line that passes. We are here, actually we moved a little bit already, a little bit more here, and time passes. And I'll show I'll quite rapidly tell you what's wrong with this idea, why this is a wrong idea about time, and in which sense it is wrong. And this will be a step sort of down into more and more general views of nature, where time has less and less property and loses its pieces, so to say, all the way to what I think is the current understanding of the structure of time, which is that there is very little time in nature. And that will be the journey, the one-way journey. And then there is the journey back, which is how from this nature at the level of quantum gravity, which is sort of the bottom level of our understanding of the physical world in sense of generality of flows, how from there we get back to this time, to the time of our experience. So it will be a long one-way and return trip where I want you to lose all your ideas of time to then sort of understand back where our common time comes from. Right? So this is the time of our experience. First of all, it's a long line. Namely, what do I mean by a long line? What do we mean? It's a sequence of moments, instant, now, before, later, which is ordered, like the English when they wait for the bus. So maybe I'm trying to Italianize you a little bit, but I don't want you to crowd for getting the next bus. That's not where I want to go. But all these instants are from a long line. They're one next to another one in a one-dimensional thing. This line it has a direction, right? The past is completely different from the future. This is one of the most obvious things and most trivial thing to say, but let me say it precisely, because then I'm going to say it's not true. The past is fixed. It's given. We remember it. We know it. We have traces of it. We have books that talks about the past. We have departments in our university that study the past, history. We don't have many departments that make a historical history about the future. There are traces in nature. If you look at the moon, there are craters that are formed by stones fell on the moon in the past. So the past traces all these traces. We have memories in our mind. The future, there is nothing like that. There's no memory, no traces, so it still has to come, right? So that's part of this idea that we have about time. Time has a metric property, namely we can talk about duration of time. This chat that I'm giving, this presentation is going to last 45 minutes, no less, no more. Certain fixed amount of time that can be measured with clocks. And we know what it means, this interval being equal to this interval, being equal to this interval, equal to this interval, and so on. And clocks measure that. And clocks are devices that are meant to tell us where we are along this line. What time is it? Where am I? Is it already tomorrow? Is it not yet tomorrow? And clocks are designed to work all together. That's the purpose of a clock. So if you take two clocks, you move them apart, you wait a little bit, you bring them back together, they still have the same time, if they had the same time. If not, it means one clock is broken, or it's not going well, or something false. This is the time, a little bit is past. This is the time of our experience. Now, what's wrong with this image? First of all, there's nothing wrong, obviously, as long as we carry on our daily life. It's a very good conceptual idea about time that works very well in our daily life. But it does not work. It stops working when we look a little bit more far ahead. And the more we look far ahead, the more this number of properties that I describe about time go away. So the main message somehow of the full talk I'm giving is that time is not a single thing. It's this multi-layered concept that has all this property that I told you. It's one-dimensional, as a metric, is oriented, is the same for everybody, is measured by clock, and so on and so forth. This, which in our intuition comes as a package, is time. It's properly thought as a combination of properties that we can dismount one by one. Time, sometimes it says, is layered, or is like a mechanism, like the engine of your scooter. You can take away one piece, the carburetor, you can take away the piston, you can take away this, you can take away that, and what remains is not the scooter. What remains is nothing at all. Right? And that's going to happen with time. When you take away this, take away that, what remains is nothing at all, because time is a combination of these properties. So let's say one properties one by one. The first one, maybe I'll mention 3 or 4 of these, let's say 4, to dismantle this idea of time. Some of this you might know, depending on how much physics you know or how much you've heard these stories already. Some you probably haven't known. Some are very solid knowledge. Some are things we suspect. I would say the first 3 are very solid knowledge. But the implications of taking all them together are strong. So first one, clocks measure time, fine, and clocks go all together at the same speed, well, that's wrong. Why is wrong? Because it's a fact that if I take 2 clocks, and if I take 2 good clocks, and I move them apart, I move one, or I bring one higher and keep one lower, and I wait a little bit and I move them together, if these are good enough clocks, they will indicate a different time. It's a fact. Okay? It was clearly understood by Einstein 100 years ago. So in a sense, we've been knowing this for 100 years. But it's recent that we actually have good clocks, not these, that we can measure this. And today with atomic clocks, with clocks that measure easily one part time with an error of 1 in 10 to the 18, 17, 18, even 19. This is very rapidly advancing the technology of clocks. So with these clocks, you can take two clocks at a different altitude of 40 centimeters, 50 centimeters, and measure that. So the clock up here goes faster than the clock down here. There's more time here. There's more time for thinking, for growing older, for everything. So there is more time in your head is older than your feet. Your head has, unless you have spent all your time upside down, in which case it's the other way around, okay? Why? Well, why is it's a funny question here. One could say why? Well, because we know from general relativity that the Earth, which is a big rock, big mass, slows down time. So mass slows down time next to it. But why? I think the right question is why not? Why is still this hard for us to digest? Because we're used to time being the same for everybody. We're used is two persons have the same age and they separate. One goes to America, the other goes to China, and they come back after a while. They still have the same age. Right? That's our experience. But that's not right, because they have aged differently depending on how they moved, depending if they have lived more up or more down, and so on. In our experience, these differences are small and smaller than our perception of time or the precision of our watches that we carry, so we don't notice that. But if we lived a little bit in the future, when I hope there will be starships going around at fast speed and coming down, we will have to confront that. So the reason for which we think that time is the same for everybody is because we got used to it by our approximation. It's like, if you grew up in the Netherlands, which is completely flat, you think that the Earth is just all at the same level. And somebody says, there are some places of the Earth where the Earth goes down. And we say, no, how can this? Yeah, it's called mountains. Wow, right? You have never seen mountains, so you're surprised. We live in a region in which this difference of time is small, so we're not used to this. If we had a big mass, a black hole not far from here, we'll be used to the fact that when you go to a black hole, you come back, everybody else has grown older than you. Good. Which means already that this line is just wrong, because the time between here and here, two events, is not fixed. It depends whether you were higher or whether we're lower, for instance. So there isn't a single time in the universe. Already there are many times. And in fact, in Einstein general relativity, you don't have a single time. You have one time per every line, per every world line. Good, that's point one. Now, point two that follow quite rapidly from that, which in fact something that Einstein realized even before general relativity, special relativity, but it has take long for becoming absorbed, because it's shocking. In my opinion, it's one of the most shocking things, and it's perhaps the most astonishing conclusion of modern physics, which is we now are here. Okay, move a little bit. What now means? What is the meaning of now? Well, I know what is the meaning of now for me. You know what is the meaning of now for you. Is it the same now? Well, obviously, yes. Because I look at you, you look at me, and I say now, you say yes now, I hear yes now, so we're in the same now, right? And then wait a little bit, and we look, we are in a new now, so a little bit moved here, but we're together, always together, the same now. But think for a moment. When we look around, if I look at you, do I see you now? Well, not really, because lights take time to come from you to me, right? So I see you sort of a little bit in the past. Now, time takes a few nanoseconds to come from you to me. So I see you as you were a few nanoseconds ago. Well, nanoseconds are irrelevant. But if you were on Jupiter, I would see you 2 hours ago. And if you were on a star, I would see you 4 years ago, the closest star. And if you were on a different galaxy in Andromeda, I would see you millions of years ago. So I couldn't say now is when I see you. And if you look at me in the moment I see you, you are going to see me in the past, in the future for me. So between the you I see and the you that see me in the moment I see you, there's an interval between the two, which is a few nanoseconds here, but few hours in Jupiter and millions of years if you were in a different galaxy. So if the people in a different galaxy want to know what we're doing now, they don't know, because they're looking somehow, there's all this time for. So one can say, well, all right, okay, this is because it's hard to check, but we can devise things to say what it means to be at the same time. For instance, I could say, well, I look at you, but I know you're at a certain distance. You are on Jupiter, but I know it takes half an hour take 4 hours light to come here. So 4 hours in the future from when I look at you, that's now, okay? Except that you may be moving fast, and 4 hours in the future could be in my own future, maybe 10 years in my future. So how can the now be 10 years in the future? It doesn't make any sense. So the more you play this game, the more you realize that it's a question which is ill-posed. There's no meaning of now outside the approximation in which we can disregard the time light goes back and forth. So what we mean by now is we both look at one another and we are in the same temporality within the resolution of time that we have. Which means that the notion of now makes sense on a radius, on a bubble around us, which has a length, a size, L, which is given by the speed of light, time, the minimal resolution of time that we can resolve, the delta t we can resolve. That's the meaning of now. There is no meaning of now outside this bubble. With our brain, without using sophisticated clocks, we resolve probably, a tenth of a second. If you're a musician, you go a bit better than that. A tenth of a second light is much bigger than the Earth. It's a big bubble around the Earth. So on the Earth, we're all in the same now. But it's just this. Proxima b, which is a closest star, has its own now. There's no sense of putting them together. You can send signals from one to the other, signal back, but in between there is no way of saying, there's no meaning of now. And in fact, people work in general relativity, theoreticians work in general relativity, study solution of Einstein equation, they know very well that there's this four-dimensional solution. There's no preferred now, no objective now that you can pick up as from physics or from anything. Why is this astonishing? Because what is it real? What does it mean to be real? Well, we are told that what is real now, right? Is the Roman Empire real? No, it was real in the past, not now. Okay, but if now is only local, is something happening on a distant galaxy real? Well, it may be in the future, maybe in the past, but if everything is real in between, it's confusing because there are things which are in the past and on the future of one another. So what does this mean to be real? After we have understood that the world works like that, namely that there is no now in the universe. There are philosophers who are discussing that. That's why I talk with philosophers. Philosophers who are discussing that and pulling each other ears and fighting. The very meaning of being real, of reality in the sense of what is real now, has to be rethought after what we have understood about physics. So the idea of one instant of time, it's completely destroyed. In our little bubble, we can talk about instants of time that we share, provided that we don't go too fast, we're not precise. But globally, there is this series of events in the universe with some temporal relation between a couple of them, but no common now at all, and no order in the mathematical sense. 2. 3. And this is a little bit more complicated and less well understood than the first two. Well understood the first part, less understood the second part. The past is different from the future, right? Where there is a local past and local future, the past is different from the future. So let's forget the other galaxies. So let's look around us. And yesterday is completely different story than tomorrow. Yesterday is fixed, we know it. Tomorrow it's open, we don't know it. Good. So I'm a physicist. I want to know, where does this distinction come from in the laws of physics? And as you probably know, the laws of mechanics don't have this distinction. The laws of electromagnetism don't have this distinction. The standard model of particle physics does not have this distinction. General relativity does not have this distinction, right? So all the basic equations of physics, quantum field theory does not have this distinction. All the fundamental equations of physics lack the distinction between past and future. But for us, the past is completely different from the future. We have books written in the past, we don't have books written in the future. So where does distinction come from? Well, there is a story about that, which is, there's one science that sees clearly the distinction between the past and the future, which is thermodynamics. And in thermodynamics, there is one law, which is the second law of thermodynamics, or the second principle of thermodynamics, that says that entropy always grows toward the future. So that clearly makes a distinction between the past and the future. Fantastic. So we have found the basic, the key fundamental grammar of the world, the elementary machine that distinguishes the past from the future. That law was written by Clausius, 19th century. But shortly later, or sometime later, Boltzmann and his friends, Maxwell also, but Boltzmann was, I think, the person with the most greatest clarity, understand that this law is statistical. Namely, Boltzmann understands that this entropy, this quantity that you can compute, in chemistry you always compute the entropy in a reaction, energy, heat, you do this calculation, you get entropy before, entropy after, and it always goes up. Boltzmann understands that the entropy is just not a fundamental quantity, but a measure of how mechanical things are disordered, right? We know that entropy is disorder, and that's a great sort of understanding that we got from Boltzmann. What mean disorder? You take a box, you have some green balls, some red balls, you put all the green on one side, the red on the other side, this is ordered. You mix everything, this is disordered. And in fact, entropy counts exactly that, how much order, how much disorder. If they're separated, there's low entropy, you do your little calculation, low entropy. If they're mixed, it's high entropy. Which makes a lot of sense, because when you shake things, they get disordered, so entropy goes up. Good. Now you look at these balls, green and red, and your friend is colorblind. So he doesn't see any order because he's colorblind, he doesn't see any order. So for him there's no order, but for you there's order. But actually it's worse than that. Your friend has a very keen eye that distinguishes some balls which are very little small and some that are a bit larger. Much better eyes than yours, you don't see this difference. So for him, order means all the little balls on one side, all the big balls on the other side. So for him, the entropy is a completely different story. So what do we mean by the order of the world? You see, I think you see clearly that order is in the eye of the person who looks. It's not in the things themselves. Order comes once, instead of recognize the balls one by one, if you number all the balls, or if you give names to all the balls, whatever way you put them, they are ordered in that particular way. Is only by distinguishing two big bunches of balls that you can talk about order or disorder. And in thermodynamics, when Boltzmann understands the statistical underpinning on thermodynamics, the key things he understands is that the notion of entropy depends on the macroscopical variable that you use to describe the system, on the coarse graining of the system, which is a simplification of the description of the system, which disappears if you look at the microphysics of the system. All right, so what does it mean? It means that this growing of entropy is tied to the approximation we make in describing a system. It's not fake, it's not illusory, but it depends on the way we have described the system, on the macroscopic way we have described the system, which in turn depends on how we interact with the system. So it's not a mental thing, it's not an idealistic thing, it's not a subjective thing, it's a very concrete thing. It depends on the way you interact with the system. The way you interact with the system is your interaction with some variables of the system, which are few out of the many, and these few determine a coarse graining of the microscopic variables and define an entropy, and the entropy grows. All this is fine. So in the future, the entropy grows. In the past, the entropy with respect to our coarse graining was slow. Why was the universe ordered in the past? Who ordered it? I mean, if you go to your little child bedroom and the evening is a complete mess and the morning is in order, you know why it's in order, because somebody put it in order. Right? But why the universe? Who prepared the universe in order? And who prepared the universe in order in the right way that looks in order for us? Mystery. Okay? What does it have to do with time? Everything. Because the distinction between the past and the future is only that, is this strange order in the past. And I want you to reflect about that, because I'm saying something very, very strong. This has been recognized by some people. Reichenbach in the philosophy of science, Russell had pretty clear ideas about that, but few. It hasn't permeated, I think, the global thinking about the order of time. Everything in our experience which is ordered in time is because of entropy. There is nothing else in the world that distinguishes the past and the future except this entropy. Concretely, any phenomenon that you can imagine where you distinguish future from past, there's some entropy. If I throw this, it stops, right? If you film it and if you look at backwards, this starts by itself. So you say, no, that's wrong. So this is a irreversible phenomenon, okay? There's entropy. Namely, there's heat. What is going on is that there's friction, and the mechanical energy of the clock goes into thermal energy of the table that is a little bit heated up. So all the molecules of the table start agitating because of the friction, and the ordered motion of the clock is transformed in a disordered motion of the molecules, right? Every time there's distinction between the past and the future is because there's heat, there's entropy, there's temperature involved. If there's no heat, no temperature, if this rolls, if you move without heat, it will go forever. And if you film and project it backward, it goes forever in the opposite direction. You wouldn't distinguish the future of the past. Any mechanical thing you can think about, pendulum without friction, you take a movie, you project it backward, is a pendulum. The solar system, the Earth and the Moon goes around. Suppose you film it, you project it backward, who can say which one is the right one? It's exactly the same motion. To distinguish the past from the future, you need entropy, disorder. Which means that the reason we have traces of the past and not in the future is nothing else than entropy. Okay? If we have a text that says something, it had to be, has had to be some entropy production, some heat, some disorder at some point. If a monk in the Middle Ages in a monastery wrote down something, and now we know something about the Middle Age because we have this text, in a world without friction, the ink would have not stayed on the paper, it would have jumped away. Right? So you need friction. The ink glues to the paper because it produces a little bit of heat that dissipates, and so is some disorder which can happen because there was a higher order in the past. So it's this high order in the past that determines the existence of traces. And we think in terms of cause and effect, cause coming first and effect becoming after, only because of the second law of thermodynamics, because of entropy. Otherwise, there could be no dissymmetry. Law of physics says that if this is connected to that, this is connected to that, both ways. We cannot say this causes this more than this causes that, because it's symmetric. Russell used to say that the notion of cause would disappear is wrong, it doesn't belong to physics, it would be recognized as something, totally useless and mistakenly considered non-damaging, like the British monarchy, and sooner or later we'll get rid of them. He was wrong, but we'll come back why he was wrong. The point is that the entire distinction between past and future is a macroscopical effect due to the fact that under our perspective, the past look more ordered. So not only the instant of time is not a line, because every line in the universe has its own temporality. Not only makes no sense to take one to talk about the now of the universe, but the distinction between one direction of time and the other direction of time is a strange macroscopical effect, which you don't see in the microphysics. 3. Oh boy, time is passing fast. I should speed up. I am going to speed up because the fourth reason for which our common idea of time is completely wrong is less solid than the first three. The first three is science that we understand very well. The fourth reason is a science that I do, so it's less solid. Why? Because I'm still doing it, right? It's not yet in the textbook. I and all my friends, we are working on. And the point is that there is a connection, which I just mentioned before, between time and gravity. Gravity, the mass affect the speed of time, but we know that gravity, the understanding we have of gravity disregards quantum mechanics. So this is the problem of quantum gravity. This is the job of my life. That's what I'm paid for, to try to write equation for quantum gravity. There are a set of equations that we have written down for describing the quantum properties of gravity, and these equations tell us something about this, what the clock measure, and tell us, I would say, 3 things. One is that anything that works like a clock cannot measure time, local time, continuously, because there's a minimal amount of time. So there's something granular in the passage of time. I understand that in the UK there is a current debate on children not being able to read analogous clocks. So they only read the digital clocks. So they come out with the wrong idea that time is discrete and is digital, right? Which is the right thing. So very good. I don't see why kids should be able to read a digital clock. I wasn't very good in reading digital clock when I was a kid because I didn't use a clock. So time is digital at a very short scale. Of course, not seconds or fraction of a second, or the Planck scale, 10 to the minus 44 seconds, very, very small time intervals. But that's a minimal time intervals. There is no smaller time interval than that. Not only that, but the clocks itself, because it's a quantum object, everything's a quantum object, can be in superpositions of different position of the handle, or different reading. So you cannot say that between this event and this event is a certain amount of time, because, as always in quantum mechanics, there could be a probability distribution of time passing from one and the other. So you see that everything you used to think about time disappears when you go to the widest possible situation, which is quantum gravity, in which you keep into account everything we know about the world today. In fact, in the equations of low quantum gravity, which is the theory on which I'm working, which brings together quantum mechanics and general relativity, in the equations of that theory, there is no time variable at all. Why? Because you don't need a time variable. You have a lot of variables. You have a lot of clocks. You have a lot of things that change. At the basic level, time is just any way of counting the change of something, which, by the way, is the definition of time that Aristotle gave 25 whatever centuries ago. Time is a number of changing. You look at something changing, day, night, day, night, day, night. You count, and this is time. Time is a counting of change. Then Newton came out with this idea, new, completely new, that time is not just a changing of something, but is some uniformly flowing something that flows irrespectively of whether there is matter changing or not. Right? It's a completely Newtonian idea. It's a new idea. It is in your mind because you studied it at school, because it's permeated our society, but it's not the old way of thinking about time. The old way of thinking about time is that you see things changing, you number them, which is fine. But Newton comes up and says, well, yeah, there is that way of thinking of time, but there's another way of thinking of time, my Newtonian way, which is that time just passes, even if nothing changes. Then Einstein recognizes that this Newtonian time and this Newtonian space, which also Newton introduced, the idea of empty space, it's nothing else but space, are actually the gravitational field. It's nothing else than the gravitational field. So Einstein, in a sense, says, oh yeah, you're right, Newton, that there is something else beside the counting of things. There is this absolute time, absolute space, but you're wrong in not seeing that these are dynamical objects. It's just an electromagnetic wave. It's just an electromagnetic field. This is a gravitational field. So it's a sort of something that fills up everything, which is the Einstein four-dimensional curved space-time. And once you realize that this Einstein four-dimensional curved space-time, which is a gravitational field, has quantum properties, it can be in superposition, is granular, it has all the funny things, it does all the funny things that quantum things do, the Newtonian time is completely exploded. It depends on the interaction, it's granular, it's different point of point. The Aristotelian time, the basic idea that you can count events, is still there. So in quantum gravity, you have events, not ordered in a line that the British, but all confused like the Italians, connected to one another. You can follow this one, this one, this one, and you can say, okay, during this blah, 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 number of things happened. So this moved a certain number of clicks, and so you can have a local notion of sequence of event, which is a minimal notion of time. And that's the only thing that remains, locally probabilistic, discrete, without a preferred time variable. Anything can work as a variable. And that's the no time, the minimal time of quantum gravity. I promised you a journey back. So I have less time remaining because I'm supposed to finish here, and we're already here, to take you back. So I hope I convinced you, well, I don't hope I convinced you. I hope I gave you a sense of the very, very weak temporal notion needed to do fundamental physics. I've written a paper whose title is Forget Time. So write the fundamental equation of quantum gravity, and if you don't see there which one is a time variable, don't worry. You don't need a time variable. Because a time variable is something macroscopic, not something down there. Down there, you have many variables, change one with respect to one another. How do we go back from there? From that basic reality, we have to find the conditions under which we live, which allow us to talk about this long line-oriented and common, which is time. And this is a number of steps. And there are many steps, different levels, different layers. Each one is interesting by itself, but they're separated. Time doesn't come up off in one step. It comes up at various levels. First of all, the granularity of time is so small, we don't have such precision, so we don't see it. This flow, we can see it continues. Fine. The quantum mechanical, the superposition aspect of time, we are big and heavy and we work at scale much larger than the Planck constant, which is what determines quantum mechanical effect, so we don't see it. So we actually see a gravitational field as a continuous thing, like Einstein described. But we live in a region in which gravity is very, very weak compared to a black hole where there is really strong. And where it's very, very weak, essentially this Einstein curved space-time is flat. And this is flat Einstein space-time resemble very much Newtonian space and Newtonian time. Not exactly, because Minkowski space, time, but very much. But we don't move fast with respect to one another, so we can disregard the time back and forth of the light, and we are so we can assume that light, instead of going at finite speed, goes at infinite speed, because in our experience, life is essentially infinite velocity. Right? We don't resolve the light travel, the time travel of light. So if time is at infinite speed, then we have the surfaces of simultaneity. We can think that we're in our bubble. And so we can talk about one single time, right? So now we have a one-dimensional line, which is still not oriented past and future. So what is it oriented at past and future? Well, let's go slowly. First of all, remember, it's entropy. Entropy depends on the way we look at the world, or the way we interact with respect to the world. So I think, and take this as an hypothesis, not as something demonstrated, some of my colleagues disagree, that what makes entropy low down there in the past, say in the early universe, entropy was very, very low, is not the fact that the universe was arranged in a very ordered way. The universe was arranged whatever it was arranged. Is the fact that we look at the universe, we interact with the rest in a way which is very particular because we are particular. We meaning we as a physical system interacting with the rest, such that under this perspective, the past was special. Imagine you take a card, you mix them. You look at them and you remember the order, okay? That order disappears when you mix again. So you see an increasing of disorder. But that order was special because you decided it was special. You looked at them and learned it. So in some sense, we are a special subset of the universe that interact with the rest of the universe in such a way that the past looks ordered to us. What is special is not the universe, is a subset of the universe to which we belong. This is called the idea of the perspectival origin of entropy, and I think it could be an ingredient for understanding why the past is different from the future. There's nothing special in the early universe. It's special the macroscopy, the coarse graining that we do. Are we done? Not yet. Not yet. And there is a last step. And to me, this has been the greatest surprise. And here I'm stepping a little bit out of my own comfortable zone, but it's what I've been learning and learning and learning. There is something about time which is still missing. And there are some philosophers, even some physicists, who says, we have got the entire story wrong because time flows, time passes. time sort of passes at a certain speed, and we don't see that in all this physical picture. So maybe there is some fundamental law of time that says, after all, there is this passing of time. I think they're right, they're wrong. And I'm, and many other colleagues of mine, including many philosophers, are increasingly getting convinced that what we refer to when we refer to this flowing of time, this passing of time, this clear feeling that we have about the flowing of time, is not in the quantum gravity, is not in general relativity, is not in quantum mechanics, is not in thermodynamics, is in the specific way our brain works. And there is an enormous amount of working today in the neurosciences, in the functioning of our brain. There's a title of a book by a neuroscientist called Dean Bonomano, a recent book in America. The title is Your Brain is a Time Machine. What does it mean? The way the brain works is to exploit this entropy gradient and the fact there are traces of the past to build memories, and in terms of this compute the future and anticipate the future. That's the basic working of the brain according to one of the hypotheses of how the brain works. So the brain is a time machine. The brain does continuously sort of grasping to some events in this confused set of events around us. We are connected by traces to some event toward the past. We are connected by anticipation on the other direction. So in our mind, there is this opening space. Okay? If you think of it, this is a metaphor of what? This is a metaphor of our memories of some of the past, and in fact that's why it's much more confused over the future, because we don't have memories of the future. When we think about time, very often we're not thinking about the physical past and the physical future, but we are considering the memories we have about physical past and the anticipation we have about the future. Philosophers have been saying that for a very long time. Husserl has been saying that. It goes back to St. Augustine, famous pages about the nature of time in his book, The Confessions. I don't know how it's translated in English, Confessioni. He says, when I listen to music, I get a meaning from a musical phrase. But I never listen to the phrase. I listen to one note at a time, right? If I listen to one note, how do I know about the previous notes? How can I get the meaning? Well, of course I know, because I remember them. But if I remember them, and Husserl is very clear in that, the meaning comes from the notes being playing now and the memories of the previous one. So it's all in the present, so to say, and it can be all in the present together because there is memory. But it's more than that, because since the brain is designed by evolution to use memory to anticipate for a purpose, because it's designed to try to get somewhere. That's how Darwinian evolution designed our behavior. Then all this is strongly emotionally charged. The passage of time is not for us a rational thing to contemplate. It's something we live into. We are this passage of time. We are this constant computing of time. You can think about reality without space. We can think about reality without things. You can think, it's very hard to think yourself in a reality without time. You wouldn't know how to start thinking. But the confusion is this because reality by itself cannot be thought without time? No, it's because our thinking cannot be thought about time. We cannot think about time. We are a time machine, not the universe. The universe is not a time machine. The universe is just a bunch of things, of events vaguely connected to one another, which in some approximation are nicely ordered. But what we think when we think about time is the ensemble of the memory and the anticipation that give us this sense that we are in this space, right? All of us. What is the real time? Real time is now, 10 minutes ago, my life, but then I've been to school, so I know about all the kings of England, so this long line, right? The line of the kings of England and queens. And so I have some extended memory, which is a cultural memory. I've studied physics and cosmology, so I have this memory longer. It's all today. It's all my knowledge today. It's all here. In the book I talk about Proust. Proust has written this fantastic novel, In Search of Lost Time. It's all about time. He says that explicitly. It's a reflection of the meaning of time. And the novel is full of stories, character, things, but the novel is presented not as what is happening in the world or what has happened in the world, but as the memory of the main character, whose name is probably Marcel. It's not clear the name of the main character. So all the 3,000 pages of Proust's novel are about what's in this, 5 inches between the ears of Marcel. It's all here. And that's the greatest intuition of Proust. To understand what is time for us, we have to look at the specific of our brain functioning more than the temporal structure of the universe itself. Of course, there's a relation between the two. I'm not saying that the temporal structure of the universe itself is irrelevant, but I'm saying that by looking only at the temporal structure of the universe, you always get the feeling that there's something missing with respect to the time of our experience. And so you do metaphysical speculation about the primarity of time, which are completely wrong, because of course there's something missing, because it doesn't pertain to the fundamental structure of the universe. It pertains to the way our brain machine works. And last point, it's strongly emotionally colored. Time is not emotionally neutral to us, precisely because our brain is a machine designed to tell the story about the past and do something in the future. We are full of motivation, right? We have hunger, we have thirst, we have ambition, we have curiosity, we have love, we have hate. That's what we are before being rational beings. And this drive is the drive of the brain that control our homeostasis and struggle to make us survive and do better, because evolution wants us to be like that. It's all oriented in time. It's all in time. So time is emotionally charged for us. Time is what brings us things we want, is the opening of the future, okay? And time is what is emotionally charged for us because it makes us lose things constantly all the time. In Buddhism, there's this deep psychological insight, I think. The main truth of Buddhism is that first is life is sufferance, but the second is that life is sufferance because we have difficulty of dealing with impermanence, with time. So time is a source of our suffering. We suffer because we lose things, or because we have lost things, or because we think we will lose things. So we're going to die. So this is the quintessential source of anxiety for humans. So time is strongly colored emotionally. And why I'm saying this? Because I think if we think that this emotional side of time is a sort of fog that does not allow us to see the real nature of time, we are confusing ourselves, because this emotional aspect of time is precisely what is deeply time for us. Time for us is this emotional connection to the event of the world that go away, that pass, that flow, that we lose. And this is the root of our strong sense of passing time and feeling time. It's ingrained in the working of our brain. This is vaguely connected to this event. It works because there's entropy, of course, because at our scale we can orient things like this. But you see, understanding time means bringing out the pieces of this layered, complex object. Time is not a single thing. It's all time for us. It's not a single thing. It's all these layers that come from approximation, from disregarding aspect of nature, from thermodynamics, from our particular relation to the world, and from our functioning of our brain, including this emotional level. Out there, the more we go general in the picture of the universe, the more time loses pieces, and there's a very weak form of temporality. And in closest to us, I think the strong emotional connection with time, the motion of time is what time is for us.